PLCs. The PLCs, if I'm in a manufacturing, we could pay $2,000 or $3,000 for a PLC, when it could be done by a microcontroller. This is probably one of the most popular ones out there. It's called the Arduino. I guess I closed my camera down, guys. Yeah, this is, let me bring the camera back up. And these little things are really slick. And they're very cheap. So if I was just going to make basic control of something that I didn't want to change very often, then probably this would be the route I would go. So this is the Arduino. This is the actual. So a microcontroller is basically a computer, but it's very limited in the tasks that it can perform. So this can't do near what a PLC can do, but it can do a lot of things, right? You understand? What it's got on this side, it's got 14 digital ports that you actually say whether you're going to input on it or output on it. So that's one of the things you define. Then there's certain pins over here. I'd have to look at the number that you can do what we call pulse width modulation on. Pulse width modulation is a very popular way of controlling the speed of a DC motor. And we'll show you all that too. Over here we have, but these are not input ports and are output ports. One thing you do when you set up your program is you tell the Arduino whether you're going to use it as an input or whether you're going to use an output. And you have to assign every pin, which is pretty neat. This is, and it's got the 6 analog ports on it. So these are analog ports. And they can either be analog in or they can be analog out. It's got a 10-bit A to D converter in it. So what that means is that when we bring an analog signal in it, we can represent it with a number from 0. We can represent that analog quantity with a number from 0 to 1023, which is pretty good for this guy this size. It powers up off a 9-volt supply, so you can run it off a 9-volt battery if you want to. It uses for years and years, and it might still be that. I hadn't bought any speakers for a long time, but just about all our speakers that we bought for our computers ran off what? 9 volts. So it's a pretty popular thing. But you can run it off a 9-volt battery if you need to. But it programs in a language. It's a scripting language, which means it's a text-based language. So this is what you get into. So this is the kind of stuff that you would actually have to learn to be able to program this. I know it's kind of small, guys, but so you have what we call variables, and you have to set up the ports. So this is saying pin mode, LED, which is pin 9, is going to be used as an output. So now pin 9 is used as an output. And then all this other stuff, they're using pulse width modulation to control the intensity of an LED. I didn't hook it up, but it's a pretty cute little program. But you can use these things to run stepping motors. You can use it to run all kind of stuff. But if you had to reprogram them, it don't program in ladder logic like a PLC does. The predominant language in a PLC is ladder logic. So if you've had motor controls, you'd pick up on PLCs real easy. Or if you've had PLCs, you'd pick up on motor controls real easy. So you can see this is not a very easy language. This is a variation of a programming language called C, which is a real popular programming language. So it's not one of these point and click things. This is actually where you go in and write the programs yourself. And when you come up here and do this, we have something called syntax. You know what syntax is? It's the written language. Syntax is the correct way of writing in a language. So we speak the English language all the time, but when we come down and we start writing, if you misspell a word, then you got a syntax error. If you don't use the right punctuation, you got a syntax error. So when you do computer programming, every statement has to be in the exact right syntax. If it's not, then when you compile it over, compiling is a technique when you take a program written in a high-level language like C and you convert it into the binary language of the computer. So all the computer understands is ones and zeros. But when I write programs, I don't understand how to write programs using ones and zeros. So normally what we have is we have what we call a compiler, which takes a language like this, which is English, even though it's hard to understand, it's easier to understand than ones and zeros, right? And then when we come over here and compile it, what it does is it converts it to the binary language that the Arduino understands. So the Arduino is not running this program, the Arduino is running a program of ones and zeros, where you have what we call instruction sets. You send it a binary code that tells it what to do, and then you send it the numbers that it works with, right? Does that make sense? Which is pretty neat. So it's got memory in it and everything. It's really cute. This guy right here, so a PLC, we get our PLCs, the 1200s, we're educational discount, so we get them for about $200 a piece. But if you out on industry, you're talking about, a 1200 PLC might cost you $1,000. This thing right here is open source. This guy right here is about $25. So if I've got something that, if I've got people that can program these things, and I can use this to run a little something, right? You understand? Then this would probably be the route to go. So you're going to run into these things. We might have these, a sensor being run by a microcontroller, and then it feeding into a PLC. So you'll run into these a lot right there. So this is called the Arduino, which is really neat. Like I said, it's open source. This language, they call it a sketch, by the way. The language, they call it a sketch. The program in the compiler is free, so it don't cost you a dime. So you can basically get this for $25 and then get the compiler. And then if you learn the language, you could get it. But even if you don't learn the language, this thing is open source, so there's hundreds of thousands of programs out there. So there might be a high probability that you will find one that somebody's written for you. So, another thing that one of the test equipments that we use, the problem with a meter, what's the problem with a meter? What's the biggest disadvantage of a meter? So nobody knows any disadvantages of a meter. Got to be some. Yeah, that's the biggest problem. They give you an average. So if we got a okay, we're laughing because Courtney's got a piece of one over here. I told him he needed to keep it. I'm gonna check it every time you take a class. I'm gonna say, "Where's that thing at, Courtney?" Yeah, so it averages everything. So if I look at an AC signal with a meter, it's going to average it out. If I look at any signal that is not that, and plus it goes to an analog to digital converter. And when it goes from an analog to digital converter, it means it takes time too. So that means if we get into a signal that's moving real fast, that's varying, what happens, your meter is constantly seeking that signal. So we've got we'll look at something. We're going to do the meter certification in this class for sure. So we'll do that toward the end. As soon as Allison gets her class through with meters, basic meters, then we'll do the meter certification program in here, and we'll bring her class over here. And in that way, she can get certified too, and then she'll be able to teach it to her class when she does the intro class. So one of the pieces of test equipment that we have that actually shows us exactly what's there, it don't average at all, is something called an oscilloscope. And you'll get into Mr. Oscilloscope when you get into AC. And you'll also deal with oscilloscope a lot in digital, because digital has a lot of fast-moving signals that we can't see with the meter. Okay, y'all understand that? So the way the oscilloscope is set up is we have what we call a dual channel oscilloscope. So if you look right here, we got two test leads that we can hook up to the thing. Y'all see this? I don't know if I can swing this around. Maybe that's upside down. So we have two test leads, if I move it over a little bit, so we can actually look at two different signals at the same time. Which there's no way in the world you're going to be able to do that with a meter. We got, one of our oscilloscopes over there's got 16 channels. So we can literally look at 16 digital signals at the same time. We would have a hard time looking at analog signals. So we got this scope, sometimes they call them channel A and channel B. Sometimes they call them channel 1 and channel 2. This oscilloscope calls them channel 1 and channel 2. So right now we just got channel 1 turned on. What we did is, we're going to go to display in channel 2. This is a digital scope, so what happens is when I turn channel 2 on, it popped up a menu over here on the right hand side of my display asking me what do I want to do with channel 2. If you don't want it, then you go over and click this button right here that turns that off. So when we look at our display, I'm going to turn off channel 2. So I just hit it again and turns it off. We call this a gradical assembly, and notice it's set up in squares. Now what an oscilloscope does is it shows us exactly what voltage is there relative to time. So time moves from left to right, and voltage is up and down. So what we can do is we can look at a signal and we can tell what voltage level it is, and we can tell how much time, if it's a repetitive waveform, how much time that takes. So I'm going to come over and take one of my scope probes. By the way, different from a meter. So what's the black lead on your meter? Is that ground? It's meter pump. It's not even common. It's meter pump. So when we make measurements in a circuit, that's what the meter makes. That's what it makes it relative to. So where can you put the black lead of a meter? You can put it anywhere you want to. In AC, it makes no difference. AC has no polarity. In DC, it just determines the polarity that the meter. If it's a digital meter, it don't even hurt if you put the red lead, if you put the black lead on the positive and the red lead on the negative. What it'll do is it'll just show you, if it's 12 volts, it's going to show 12 volts. It's going to be negative 12 volts. AC, it means absolutely no difference. AC has no polarity. So you see people, they'll try to correct you and say, well, you're going to need to put that black lead on your neutral, not in AC. It makes no difference. On scopes, this is ground. True ground. That's our ground. So where can you probe this? You can't put this sucker anywhere you want to. So we're going to make this reference to circuit common or circuit ground, right? You understand? So all the measurements on your scope. So you cannot take an oscilloscope and probe inside a circuit. So I can't measure the voltage drop across R1. But I can measure the voltage into R1, and I can measure out of R1, and I can subtract them, right? You understand? Or we can tell our scope to subtract. So we have the ability to do that too. So I can use two probes, and I can hook one probe on the input of R1 and hook the other one on the output of R1 and tell my scope to do what? To subtract. But it takes two probes. You can't use this. This black lead right here is always referenced to where? To ground or common. Wherever I put it at is common. It's now grounded. So even if I get it in a circuit that's ungrounded, as soon as I put that in there, then that circuit is grounded. So normally we put every one of these on the common of the scope. So this is, so if I was to come over right here, so this is my function generator. So if I was to take this black lead and hook it up to the red lead, I just shorted out my function generator. I understand that. So I'm taking my ground and putting it on the signal lead of my function generator. So that means on this thing I got to go what? Black to black, and then my scope goes up. And then my scope comes up and starts showing me something. Okay. Now, what we're doing is, what do I want to do? Do I want to make this thing closer together, or I want to spread it out? Well, if I make it closer together, it's just going to get, I mean, what I'm looking at is I'm looking at a signal. And I'm looking at right now we're looking at a sine wave, but I can switch it over to digital. So where's my PowerPoint at? Don't tell me I closed that down. That too. Sorry. Well, it's not smaller. What we're doing is what we're doing, and what you got to understand is we're looking at a waveform that looks like this. But the problem is I keep making it smaller, and I keep getting them closer together and closer together, and I end up with something that looks like that. When actually I want to look at something like this, right? You understand? So the problem is I got them so close together, my eyes are just blending together, and it looks like a solid bar. So anytime you see something like that on the oscilloscope, it means the oscilloscope is we need to spread it out, right? Does that make sense? Now what we're doing is we set what we call a time per division. So the smaller I make the time per division, the faster it's going, so it would do what? It would spread it out. The less time I put per division, everything gets closer together, right? You understand that? So what we have right here, this control right here, there's my camera. So this control right here, so here's, and they're boxed in. So these two right here is what I do to control the voltage, right? So this is channel 1, channel 2. And this over here says horizontal. Well, horizontal is this one, right? You understand that? And it's got down here, it says M is horizontal. It says I've got 25 milliseconds per division. Well, what I'm going to do is I'm going to come up here. Now it's 5 milliseconds. Now it's 2.5 milliseconds. Now it's 1 millisecond. And notice we're starting to see something, right? Here's 100 microseconds. Here's 10 microseconds. And then sooner or later, by George, there it is. So what happens if you look in there and you see this big old bar going across your oscilloscope, it means it's going way too slow, and you need to do what? Speed it up by decreasing the time per division. So if I decrease the time per division, it means it's going through the divisions faster. Okay, you understand that? But what do I need to do now? Well, I need to make it bigger. So our ultimate goal to using the oscilloscope is to make this as big as we possibly can make it. And then plus, this is AC. I would like it to be in the center, right? So what we got is we got a little thing over here on the left-hand side that says 1. Well, that's channel 1. But what I'm going to do is I've got this control right here called position. So notice when I start moving my position, it starts moving up where? To the center. So there it is. Okay. Now I want to make it bigger. Well, what I'm going to do, just like we have time per division, is I'm going to come over here and change the volts per division. So what I'm going to do is I'm going to make the volts per division smaller. So if I put 1 volt per division, and if I got 5 volts, it's going to go 5 divisions, right? If I put 5.5 volts per division, and I've got 5 volts, it should go 10 divisions, which it can't because we only got 8. So I'm going to make my volts per division smaller. And what are we trying to do? Well, we're trying to get it. Now look at it. It's kind of strange, right? In fact, let me do this. What's going on? Well, it appears that the oscilloscope is jumping all over the place. Well, the problem is I'm looking at a waveform, and I'm taking pictures of it, and it's not synchronized, the scope is not synchronized with the waveform that I'm trying to look at. Okay, y'all understand that? So the final control we need to understand. You see there's a lot, because this is a computer. It's called a trigger. So you notice when I do that, can you see the white line appear down at the bottom? So right now I'm synchronizing with nothing. See it right there? Well, watch, as soon as I get my scope up into the waveform, now my scope can see the voltage when it changes, and everything should freeze. What's going on? Function generator. Not scope. So see, as soon as I get this out, see, can y'all see the white line? Okay. So if you look on one of these things and it's moving around like that, what does it mean? It means the scope is not synchronized with the signal, and you just find the trigger. And then what I like about this scope is it shows you once you get inside the waveform. And as soon as you get inside in the waveform, now it's synchronized and it just does what? Now it freezes. So what's it telling us? Well, what it's telling us is it's telling us the time. So see, that's not good because I've lost it. If I go down here, I'm putting too much information. So what we're trying to do is make it as big as we possibly can do it and still see it, right? Y'all understand what I'm saying? So how many volts do I have? Well, right now I have it on 5 millivolts per division. I'm sorry, 500. So that would be 500 millivolts, right? When we talk about divisions, we're talking about the major divisions. Can y'all see it? So this would be 500 millivolts. This would be 1 volt. This would be 1.5 volts, and then that would be 2 volts. That makes sense? And if it's 500 millivolts, that means each one of these minor divisions would be worth 100 millivolts. There's 5 of them in there. Does that make sense? Now the time. So what we need to do, first of all, when we measure this, let me change this a little bit. I'm going to raise the output of it. Now it's real hard to measure because I've got minor divisions at the top and minor divisions at the bottom. So what do y'all think I should do? Well, what I'm going to do is I'm going to take my position. I have control of that, and I'm going to put the bottom on a line. Now I got something to reference from, right? So now I've got 1, 2, 3, 4, 5, 6 point. I've got 6.1 division. That's not true. I'm counting in ones. So it'd be 0.2. Huh? Well, no, I'm counting in divisions. So if I'm counting in divisions, I'm counting in ones. And if I take a 1 and divide it by 5, then it comes up and gives me 0.2. Right? Y'all understand that? Yes or no?
No, right there.
What do you mean?
Count 2 into that next division.
No, let's move it over. I don't know what you mean on top of it. I'm going to move it over. Okay.
Talk about P.
What do you mean the P? This is the P. Yeah, so that's one minor division.
Okay. It looks like P.
It does.
No, back here.
Here's 2 right up here. All right, well, let me get out of the way. So there's 2 right there. This is 3, 4, 5. Okay. So I've got it on 500 millivolts per division. 1, 2, 3, 4, 5. Point 2. Because, okay. So what would I measure? Well, until you learn a scope, you notice me, I could do it in my head. But what you would do until you learn it is you'd say, well, how many divisions do I have? Well, I've got, what do we say? I've got 5.2 divisions. And each division is worth 500 millivolts. So I would just multiply them out, and that would tell me what I'm actually measuring. So what are we actually measuring? 1 point, what? 1.7 volts? No, 1.6 volts. I'm sorry, 2.6 volts. 2.6 volts. So this is what we do on a scope. If I looked at this with a meter, What you mean instantaneous?
What's this instantaneous voltage?
Instantaneous voltage would vary depending on where you're talking about. So you really don't have an instantaneous voltage. So the way this works is that this is generated on a circle. So we call one cycle equal to 360 degrees. And what we would do is if I call this 0 and I was to come over to some angle, like if I was going to come over to like a 30-degree angle, and then I drop that, and then I come over here and bring it back to 0, it forms a right angle. And if I want to find this right here, this length, then I can take the sine of the angle, like 30, the sine of 30 degrees is equal to 0.5. So that means if this right here was 12 volts, then at 30 degrees, it would be at 6 volts. So why do they call this? This is why this is called a what? It's called a sine wave, because the instantaneous voltage varies with the sine. If you look at the sine of 90, the sine of 90 is 1. So 12 times 1. So what I do is I take the sine of 30 times the maximum voltage, which would be 0.5, which would give me 6 volts. The sine of 90 is 1, so 1 times 12 is 12. The sine of 180 is a minus 1. So if you multiplied 100, the sine of 180 times 12, it would say minus 12. So it's really, really neat. A lot of people think that sine wave, if you say this is 90 degrees, when do you get half? Most people will say 45. But 45 is actually 7.7%. It's actually almost 71% at 45 degrees. So 30 degrees would be half, because it starts off and then it rounds off toward the top, right? Yeah, the sine of 180, I'm sorry, yeah, the sine of 180 is 0. So the sine of 180 is 0. The sine of 270 is minus 1. The sine of 360 is what? The sine of 360 is... Oh, y'all taking AC now?
Yeah.
Now, what we can do with the time is that the time is if we know the time, we can calculate the frequency. Now, we don't let y'all do it. This scope is a computer. This is a digital scope. So if you actually look at the waveform, you can see it's set up in hundreds of little old tiny steps. So what's the time? So the time, I have it on, so what I'm going to do on my time to make it easier to read, time goes from left to right. So if I want it to go from left to right, what I'm going to do is move where it crosses over to a vertical line. And then I'm going to count division. Now this is easy. So I've got 1, 2, 3, 4, 5, 6 divisions. I got it 10 microseconds per division. That's 600 microseconds. But we would still do the same thing. So if it was 6.4 divisions, then I would take 6.4 and multiply it by that, right? And then if I want to know the frequency, I would take the reciprocal of that. Time and frequency are opposite. So what's my frequency, guys? I got exactly 1, 2, 3, 4, 5, 6 divisions. I'm going at 10 microseconds per division. So it'd be 6 times 10, that's 600. By the way, this is on the next test, according to paying attention. So what would be the frequency? You got your calculator? Huh? 1.67? Now, well, no, this is hertz. This is cycles per second. Not megahertz. This function generator won't do megahertz. We do have one over there. We'll do it. So that's one thing you're going to have to. No, no. A millihertz. First off, it's almost anything that we do. If you ever come up with millihertz, you know it's wrong. It's going to be hertz. Okay. So I'm going to come up here and take 600 microseconds. So that's 600 times 10 to the minus 6. And then I'm going to take the reciprocal of that. Why would I multiply by 10? Why? Well, no, this scope actually has 12. But we're counting the number of divisions, right? Well, no, that's how many is available to you. So this would be, the divisions would be like the range on the meter. So if I got a meter and it's measuring 5 volts, you say, well, it'll measure up to 600. Do I need to multiply that by 600? No. What we have is we have 12 divisions that we can measure with it. All I do is count the number of divisions. So I'm going 1, 2, I understand what you're saying now. So I'd say one, I did it in my head is what I did. So I've got 1, 2, 3, 4, 5, 6 divisions. I have 10 microseconds per division. Well, see, I can do 6, right? So we got 6 divisions, 10 microseconds per division. So what is that? That's 60 microseconds, right?
That's 6 starting from.
Micro, not just 60 micro. Go ahead.
How does it work? It's 6 from peak to peak.
No. It don't make it. When you're talking about time, time goes this way. Now, literally, you can measure at peak to peak, but peak is hard to see. So normally, yeah, I can measure the time to that peak to the time to that peak, and that would give me the same frequency. Normally, we don't do that because it's hard to get it exactly on peak, right? But it's real easy to get it on one of these lines that's making this change, right? Understand?
But if you have a problem.
So the first thing I did was I moved it over to a vertical line, so now I have a reference point, right? Then I count the number of divisions. 1, 2, I thought it said 100. I don't have my glasses on, but it says 2. It says 1, 2, 3, 4, 5, 6 divisions. 10 microseconds per division. That means it's what? 60 microseconds.
It's the same, but what I'm asking is if I have a problem on the test, and it's giving peak to peak, I could use that peak to peak.
No, your peak to peak is a voltage, it's not a time.
But I could use, oh yeah.
You said if I said I had 60, if it was worded like this, if it said I had 60 microseconds between the peaks, then you could do the frequency. If it says the peak to peak voltage is 15 volts, so peak to peak is a term we use for voltage, right? You understand? Normally, when we measure time, we don't try to do the peaks because the peak is not well defined.
I understand.
I mean, to get that time between peaks, I would have to get it exactly on this peak and measure it exactly to the other peak. But literally, you can count. So I can come up here and deliberately, move it way down here. Okay? And I'm going to come over here and now I'm going to get this at a crossing. And I'm going to see where it crosses going down over here, and it's still 6. So on the edges, you can literally measure time anywhere on the edge, but you don't want to try to do it at the what? At the peak, because the peak is not well defined. That makes sense.
I was looking at something.
Yeah. So you're getting a peak to peak is not a time, it's a what? It's a voltage. Just like,
Just digging in on the AC and going.
well, the scope is a new piece of equipment, and this scope here has all types of features on it. But I could go in and get one of our analog scopes in there, and it would have exactly this same feature. So it don't make any difference how complicated the scope is. It still has volts per division, time, and trigger. Those are the main two things that right now in AC you need to really understand. Later on, when you really get into scope, this is a storage scope, which means I can literally come up here and tell it to store. And then I can come up here and I can disconnect the input now, and it stores that. And then I can take that information and save it on a USB drive, on a thumb drive down here. And I could literally, I could literally take this scope and measure in a good system, save all these measurements, and then go out and troubleshoot a bad system, and I have a set of what? A good one. Yeah. It can do math for us. It can do all type of neat stuff that. Well, yeah, we got a $100,000 scope over there, but it's a combination of an oscilloscope and a logic analyzer. So you got you can get handheld scopes that you can hold in your hand. That's a meter and a scope. It's all in one, but the display's fairly small, but it's a handheld meter. And you just can slip it between an oscilloscope and a voltmeter. Yeah, if you got some money. Well, you're up in about the $1,000 range. So, like, guys, let's change this up a little bit. I'm going to change the voltage. Oh, I'm sorry, I got it stored.
Yeah. Put your probe back on. Oh, you got it on.
Yeah, no,
Probe?
Yeah, it's back on. So. And let's see if we can figure this out.
Probe up one.
Yeah, I did. I unscrewed it right here. Oh. Yeah. No, something's wrong. We, what you have though, I don't know if you see this, when you start using the oscilloscope a lot, what happens all the time, it's like when you have 3 meters out there, you constantly get the meter leads swapped up. So normally what you do is you get a piece of masking tape or something and put it on both ends. This scope came with a bag of identifiers. Yeah, so normally what we do is we use this for channel 1 because it's blue and yellow, and we use this one for channel 2, but it comes with green and all different types of colors that you can use. So right now I've got it hooked up to channel 1, and I have channel 2 hooked up. Not still up there. And it's a computer too, so what is it? Gets locked up every once in a while. Oh, by the way, this got a frequency counter on it, so y'all calculated 16.7. It was actually 17.1. But you got to understand, your scope don't have the resolution that this guy here. This is actually a frequency counter, so it's literally counting the frequency that's there. So if I got to have my frequency exact, I'm not going to use an oscilloscope. I'll use a frequency counter. But if I want to see, okay, a pretty good estimate. So if I looked at Alabama Power, it came up and measured, 16.8 milliseconds on my scope, and it came up to be, 58 hertz. I know it's 60 because Alabama Power monitors that frequency, like everything.
Why do they monitor that?
Why do they monitor the frequency? When we get into AC, we get two types of opposition in an AC circuit. We got what we call resistance, which is R, and then we got what we call reactance, which depends on frequency. And the two types of reactance we have is something called X of L, which is equal to 2 pi FL. And then we have something called X of C, which is equal to 2 pi FC. Now the big thing right there is that right there. So all the X of L's and X of C's in the power grid are matched to 60 cycles. If you get away from 60 cycles, and your transformers are going to either pull more power or not enough power. All your motors are going to run at different speeds. So they're more concerned with the 60 cycles than they are with trying to get exactly the right voltage to your house. So if you ever get on it, if you wanted to see 60 cycles, just get on Alabama Power and by George, that sucker's what? 60 cycles. If you went over to Europe, it's 50 cycles. So over in Europe, but their transformers and everything match. But if you took an AC motor from here and went to Europe, it would run at a slower speed. It wasn't running at its rated speed. It'd run it for 50 hertz. So one of the main things that sets the speed of an AC motor, which we'll look at later on when we look at motors, one of the big things that sets the speed of an AC motor is the frequency. But the big problem we have is these guys right here. They both vary their opposition with what? Frequency. And all your transformers are X of L, all your motors are X of L. So if you let that frequency get off, if you let it go down, your transformers are going to be less efficient. If you let it go up, it'll change everything, yeah. So frequency is pretty much well perfect. In fact, a long time, and it's still true. So if you've ever got a clock that resets when you turn off power, odds are it's timing off Alabama Power.
You know, I used to get those the atomic clock plug when they set themselves.
Yeah. Well, they're setting themselves off the atomic clock out in Colorado Springs.
I mean, it's still setting sometimes.
No, what I'm saying is that if you've got a clock that when power fails at your house and it comes back on and it just sits there and blinks, odds are it's timing off Alabama Power. Because Alabama Power is so, and it's 60 cycles per second, all you have to do is divide that by 60 and you got a nice timing waveform, right? Okay, guys, so here's my voltage and here's my frequency. Let's do this and then we'll come back and take a break.